Okay, so we continue with the charges appearing on the wire. If you go to the trolley frame, we started with a wire in which there is a current, and current is due to this negative charge line which is moving with velocity v, and then there is compensating positive charge line, so that this wire is neutral in the lap frame and no electric field there. Then you go to that trolley frame, and in this trolley frame you see that the charges are now, charge densities are different. The positive charge density is more and the negative charge density is less, and therefore, there is an unbalanced resultant positive charge density. And our dilemma was that if there is no electric field here, if I place a charge q here and move this charge with velocity v, then since there is no electric field here and therefore, there should be no force, we do not know about magnetic field. So, it should stay here at this separation. Stay here means it is moving, but this separation should stay at this value r. But now, if I see from the trolley frame, there is a positive charge density on the wire, there is an electric field, there is electric field in this direction, and therefore, there is a force, and this distance keeps increasing. Now, this is very illogical. If this distance is increasing, then it should increase from both frames, because it is a perpendicular distance. Then this direction, the trolley and the lab, they are moving with respect to each other in this horizontal direction on the board, but then this perpendicular distance, this should not change, or if changes, it should change in both the frames. So, that compels us to tell that yes, there must be a magnetic field, there must be a field other than the electric field which is exerting force on the charges. So, let us go ahead with this. How much is the charge density? Let us see how much is the net charge density. This is not equal to 0. How much is this lambda prime? So, let us calculate that. So, it is lambda plus prime and then plus lambda minus prime, and lambda plus prime is here. So, net charge density, linear charge density of course, on the wire as seen from the trolley frame is lambda prime, which is lambda plus prime, and that is lambda naught divided by square root 1 minus v square by c square, and then minus this other one. So, minus lambda naught into square root 1 minus v square by c square. That is the net positive linear charge density as seen from the trolley frame. Now, if you simplify this expression, you take 1 minus v square by c square here in the denominator, this is lambda naught here, then minus lambda naught into this, that is 1 minus v square by c square. And how much is that? This lambda naught cancels with this minus lambda naught, and you are left with lambda naught v square by c square, and then divided by square root of 1 minus v square by z square. So, this is the positive charge density here. So, at distance r, what will be the electric field? This positive charge density, linear charge density will create electric field everywhere. So, how much is the electric field here at the position of this charge, which is now at rest, in the trolley frame. Okay, so, that electric field at the location of charge q, location of this charge q which is at a distance r from this line. So, you know the formula, it is lambda divided by 2 pi epsilon naught r. This is the general formula for that, and here we will put the linear charge density which we have obtained here. So, it is lambda naught v square by c square divided by 1 minus v square by c square. So, that much is for lambda, and then 2 pi epsilon naught r here. So, 2 pi and epsilon naught and r here. So, that is the electric field. And how much is the force? How much is the force in this trolley frame? Charge is at rest, you have a positive charge density which is creating an electric field. So, the force is q times E, and that will be equal to, force is q times E, and that will be equal to q here, and let us bring one v here. Let me rewrite it slightly, and then what is left, lambda naught by c square. So, I write lambda naught here, and then by c square. So, this is 2 pi epsilon naught and then c square, okay, and then what is left, 1 v is left, and then this 1 minus v square by c square, square root. So, let me write it this way, q times v times, and then I write lambda naught v here, and then 1 by epsilon naught c square. Remember what it is, 1 by epsilon naught c square. This is mu naught. This is mu naught, permeability of the free space, and this is permittivity of the free space. So, this is the exact relation between these two. So, this we can write as mu naught. So, let me write it mu naught here, mu naught here. So, this epsilon naught c square I have written, and divided by 2 pi here, 2 pi here, and r, this r I had not written. So, this r is here, and 1 by square root 1 minus v square by c square. Okay. So, that is the force on the particle in the trolley frame. So, there is some force transformation that will give you how much is the force in the lap frame, right. In relativity, and just like length contraction, you also have transformation equations for forces. So, if I know the force in the trolley frame, I will know the force in the lap frame. So, there is some transformation formula. Nevertheless, you can see that if this is the force, this will go away once you go to that frame. So, if this is the force in the lap frame in which the charge is moving. Now, let me draw it from the lap frame. This whole picture here and whole description here, whole calculation was from the trolley frame. So, if I come back to the lap frame and erase all these things from here, force from on the charged particle as seen from the lap frame. And that will be q into v and into lambda naught v divided by 2 pi r, 2 pi mu naught here, 2 pi small r. So, I have written q and then v, lambda naught I have written, mu naught I have written, and then v I have written, and 2 pi r. So, this will be the force. This much force must be there in the lap frame, but in the lap frame, In the lab frame, there is no charge density, there is no electric field. In the lab frame, what is this picture? The picture was that the positive charges are at rest, the negative charges are moving. So, there is a current. So, there is a current here, this is moving with velocity v, and the charge densities were same, lambda plus equal to lambda minus, and that is equal to lambda naught. So, there is no electric field, but the force is there. So, there has to be another kind of field which exerts force in the lab frame, and you can recognize what it is. What it is? Lambda times v, this will be your current. This will be your current. Remember, if you have a charge, linear charge density, and then you take some dl and then ask how much is the charge crossing from this side to that side, and from there you calculate what is the current. So, this is that current lambda naught times v. So, it is q, and the charge is, remember, the charge q which is here at a distance r is moving with velocity v. This is our lab frame picture. So, q times velocity, and this is mu naught times capital I by 2 pi r. And if I call it b, it is q times v times b. And what is the direction? The velocity in this direction, force is in this direction, because the separation is increasing. So, the force is in this direction, the velocity is in this direction. So, you can see that it is a relativistic requirement that the magnetic field must exist if there is a current. If charges are moving, they must produce a magnetic field, and if they are producing magnetic field, that means you are seeing the relativistic effects in the normal lab conditions. All right. So, this much about the relation between this relativity and magnetism. So, now what I will start is, there are three things that we should know before I start. One is the force. With all kinds of experiments that our ancestors have done with electric field, magnetic field, currents, we know that the force because of magnetic field on a charged particle is q times v cross b. So, first thing is that this v is velocity of the charged particle in the magnetic field B. We will use this symbol B for magnetic field. So, there are certain things that you can immediately see from this. If V is 0, if the charge is at rest, then even if there is a magnetic field, the magnetic field will not exert any force on this. So, magnetic field exerts force only on moving charges, right, and the same charge can be called moving from one frame and at rest in some other frame. But then the electric field and magnetic field, they are interchangeable as you change the frames. So, taken both together, the things become consistent. The electric field, the force due to electric field is q times E, and if both the fields are present, electric field as well as magnetic field, then you have force is q times E plus V cross B, and there is a name for it, it is called Lorentz force. So, electric field can exert force on any charge, moving or not moving, and that will be q times E, but the magnetic force will only be there if this V is not 0, it is there, the charge is moving, and then this is the expression. Okay. This equation tells that this magnetic force is perpendicular to the velocity, it is a cross product, and also perpendicular to the magnetic field, right. It is a cross product of two vectors is perpendicular to each of the two vectors, and therefore it is this. Now, this has a very interesting consequence, because you know that the work done by a force in a small time interval dt is given by f dot dr. So, if you have a particle which is moving, on this path and there is a force on it, then in any time dt when it goes from here to here, this is that dr, and in this time interval how much is the work done by that force. So, force dot product with dr, that is the work done by definition, and this is equal to change in kinetic energy. From going from here to here, if speed changes, then the kinetic energy changes, and this quantity is same as the change in kinetic energy. Now, this dr you can write as f dot v dt, v vector and then dt, because v is nothing but dr dt. That is the definition of velocity. If you have a small displacement dr and then it takes time dt, you divide, take the limit dt going to 0, that is velocity. So, v is dr dt. So, you can write this dr as v dt. Now, if f is perpendicular to v, f dot v is 0, and if f dot v is 0, then this delta k is 0, and if delta k is 0, that means the kinetic energy here and the kinetic energy here are the same. So, the speed here and speed here same, because your kinetic energy is half mv square, mass times velocity square, and therefore, if kinetic energy is not changing, if delta k is 0, if this is 0, then this speed remains constant. So, the magnetic forces will never change the speed of the particles on which they act, right. So, magnetic forces or magnetic field cannot change the speed of the particle. It cannot speed up things, it cannot speed down things, the speed remains same under magnetic fields. Magnetic fields cannot change the speed, but magnetic field exerts force, and if force is there, acceleration will be there, and if acceleration is there, then this velocity should change, dv dt, acceleration is dv dt. So, if the force is there, you have acceleration in the same direction, f equal to ma, and that means this v is not constant, this v vector is not constant, but speed is constant, that means its magnitude is not changing, and so the direction must change, right. So, magnetic fields change or deflects, magnetic field deflects the particle. Deflects means it is going in certain direction and the direction changes, it deflects from its path. So, magnetic field can do that, but it cannot change the speed. Now, the other thing is this force is perpendicular to B. This is also interesting. This is also interesting, especially if you compare with electric field lines. If you talk in terms of field lines, just like electric field lines, you can also talk of magnetic field lines, and that means if there is a curve, so that tangent gives the direction of field, then you call it a field line. a curve so that at each point the tangent gives you direction of magnetic field is known as a magnetic field line. You must have done this experiment, a bar magnet here, and then with proper orientation you place a compass needle, look the direction and then put points here, then put compass needle at this point and so on, and then you get this kind of curve, this kind of curve. This kind of curve you get. So, these are the field lines. You have a direction here on this lines, so that here the magnetic field is in this direction, here the magnetic field is in this direction, here the magnetic field is in this direction and so on. Okay. So, an electric field also you must have at least studied, if not drawn experimentally. It is more difficult, minus q plus q or any charge distribution, and then you have field lines are like this, field lines are like this. Now, here the force is parallel to the electric field. So, these field lines are also force lines. In fact, they are called lines of forces. The electric field lines are called electric lines of forces, because this is also the direction of the force. This is the direction of electric field and this is also the direction of force. So, these are lines of forces, and sometimes people do use this same terminology here, magnetic lines of forces, but this is not lines of forces, because if the magnetic field is in this direction, the force has to be perpendicular to this, F has to be perpendicular to B. So, you can draw magnetic field lines, but they will not represent the force lines. The force is perpendicular to the direction of the magnetic field. Now, units, let me talk of units and then we will stop. The SI unit of magnetic field is called Tesla. And if you start with, say, F is equal to Q V cross B, then this is Newton, SI unit Newton, here SI unit is Coulomb, velocity is distance by time. So, it is meter by second, and then this magnetic field, then the unit of magnetic field. And so, the unit of magnetic field is N Newton, S here, then meter here and Coulomb here. And what is Coulomb by second? Coulomb by second, this is current. So, this is Newton ampere per meter. So, that is SI unit, and this is given a separate name, that is Tesla. Now, this Tesla seems to be a somewhat larger magnetic field, a strong magnetic field. The Earth's magnetic field is about, say, typically Earth's magnetic field is typically 50 micro Tesla or so. The magnets which are generally used in school laboratories, they are also having similar kind of magnetic field in front of their poles. As you go away, of course, it falls very quickly. So, that is this, but then it is not very large. This Tesla is not very large nowadays. Nowadays, you have magnets, the iron, niobium kinds of magnets, rare earth magnets, which easily produce magnetic field of the order of 1 Tesla just in front of their surface. The maximum field produced by these magnets, very commonly used, is 1 Tesla. but then if you want to get 10 Teslas, 20 Teslas, then yes, huge arrangements are to be done, large currents are to be you have to generate in large coils, and then you have all cooling arrangements and superconducting coils and so on. So, this is the kind of units this magnetic field is there. So, our next task will be how is the motion of a particle if it is given an initial velocity in a pre-existing magnetic field. So, we have some magnetic field created by some currents, and then we start a particle, charged particle in that field, and then onwards how it moves. So, motion of a charged particle with a given initial velocity in a given magnetic field. So, that is the chapter, that is the section, that is the topic that we will be doing in next few lectures.